Hello, everybody. First of all, I would like to thank Anders and also to Elena for this kind invitation to present this seminar today in front of you. It's really great to be in Melbourne. I always enjoy, even if the travel from Germany is like 24 hours. Yeah, as Anders introduced this seminar, this topic, I'm going to speak about infrared nanoimaging and nanospectroscopy. I'm going to make a very brief introduction in the technology to explain how we can overcome this diffraction limit of the light to be able to measure the optical properties of materials with nanoscale resolution. And then in the second part of the talk, I will present some applications which I believe could be of interest for the users of this facility. Okay, during my talk, you can anytime ask questions. I see that quite some people are online, so feel free to write in the chat, and I'm happy to answer the questions during the presentation. All right, so I know that many of you are experts in AFM, atomic force microscopy, and you are aware that AFM provides an excellent spatial resolution, but unfortunately there are no optical or chemical information while scanning a sample. This is, by the way, a DNA and white blood nucleus imaged with AFM. In the same time, you might be aware that vibrational spectroscopy like FTIR or Raman provide very important information, analytical data, because these are techniques which are sensitive to molecular vibrations. And this is a typical infrared spectrum that is measured on polymer. The drawback of these techniques is, of course, the relatively large measurement area. So with the classical FTIR or Raman, you don't get this nanoscale optical resolution. Now, there is a way to combine these two techniques, and this can be done in a nano IR or SNOM instrument. And how this combination of the two techniques works, I'm going to present in the next slide. Here, you can see an AFM tip, which is metallized in contact with a sample. And in addition, there is a laser which is focused here on the tip. And this tip works like a small nano antenna. It's going to focus the light at the end. So it generates a small, ultra small nanofocus. And with our microscope, we are able to detect the light which is coming from the material under the AFM tip. And this light is detected with the help of a microson interferometer. This is a sketch here. And by doing this interferometric measurement, we are able to obtain the complex optical function, the absorption, reflectivity information of the material, and everything is, let's say, recorded or measured with a resolution of about 10 nanometers. This is the size or the radius of the AFM tip. And it doesn't matter the wavelength that you are using in this setup. It can be infrared, but in the same time, it could be even visible light or terahertz. The resolution, the spatial resolution of this measurement, it's given by the tip radius. Okay, just to understand a little bit better the setup, one of the main measurement modes is imaging, nanoscale imaging. And here we can see this kind of microson interferometer, which I mentioned earlier. You see the light coming from the laser, and then here is a beam splitter Some of the light is focused by the parabolic mirror to the tip, and the same parabolic mirror is collecting the light and goes to the detector. And here you have a reference mirror, the same like in a classical FTIR microscope. In this case, it vibrates, and it allows us to measure simultaneously not only the, let's say, the AFM properties, but also the optical properties of the material. So when you are scanning the sample, pixel by pixel, you get, in this case, this reflectivity map and the absorption map. This is a polymer blend, so you see very nicely contrast. And this contrast depends, of course, on the wavelength or the frequency of the infrared laser. So, of course, if you tune the laser emission to a different wavelength that is not absorbed by a material, then you will see the same area with a different contrast. So this is, let's say, kind of a chemical mapping that we can achieve on such a polymer sample. Okay, yeah, this is a background free image. The scan size is 5 by 4 micrometers. But to get a feeling about what would be the tuning range of the laser, what can you achieve? I want to show you this image here. We are using nowadays quantum cascade lasers or OPO lasers. It's not that important, the name, but what is important, it's of course the tuning range. So for this particular laser, OPO, it's possible to tune the emission from about 600 wave numbers up to 7,000 wave numbers. And you can see here a material that is actually silicon dioxide and silicon. It's a test sample. And when you make this mapping of the material at different wavelengths or frequencies, in this case, you see how the material contrast is changing. Okay, this is another image I want to show you. This one illustrates a typical measurement time. This is about 3 milliseconds integration time per pixel. Of course, if you need to make to have a better image quality, depending on the material you are scanning, you can increase this integration time. This is a large image. This is a 20 by 60 micrometer image. This is recorded with so-called AFM-IR measurement mode, measuring the photothermal expansion of the material as a function of frequency. And this is again a polymer blend. It's a mixture of polystyrene and PVAC. In this channel here, you see, of course, the topography. The height is changing by about 10 nanometers, but it's the optical channel which provides the characteristic contrast. And you see that in one case, making an image at 700 wave numbers, you are hitting the PS, polystyrene absorption line. And by tuning the laser to this frequency, 1266, you are inverting the contrast because now you are exciting the absorption line of the PVAC. Okay, I hope everything is clear so far regarding this kind of mapping. Are there any questions? If not, then we can go next. This is also about, of course, nano IR, but it's spectroscopy. You can use also broadband lasers, and these are some typical spectral ranges, coverage of the lasers. It's possible also to use a synchrotron infrared radiation for this measurement. So it's the same working principle. The difference is that when the reference mirror is moving, we are recording so-called interferograms. These are measured in specific points on the samples, and the Fourier transformation of these interferograms give directly the absorption and also the reflectivity spectra of the material of interest. So these are measured simultaneously. Okay, so just a short summary. We can say that this technology is able to provide nano imaging, but also nano spectroscopy characterization of materials with nanoscale resolution. Now, we are on the second part of the talk, and here I want to present some applications of this technology on different classes of materials. I'm not going to speak about all of them, just to highlight it's possible, of course, to measure organic materials, as I presented on polymers, but also biomaterials, organic semiconductors. Some people are interested in inorganics, in oxides, minerals, 2D materials. It's an important class, but also study and map electric fields in metals, in antennas. But I think this is a topic which is not so interesting for the audience. So I will present mainly these applications on organic and inorganics. But basically, any AFM ready sample which has a roughness of less than few micrometers can be imaged with this microscope. Okay, one example that I like to show is some measurements that I did for a company, for a tire company. And in this case, the question that we had to answer was, how is the distribution, the special distribution of these three materials, styrene, butadiene rubber, silicon dioxide, and natural rubber, in the tire? We know that all of these three constituents are distributed somewhere in homogeneous distribution, but from the AFM, from the height information, of course, you don't know where these three constituents are. So all of these three materials, they have different infrared spectra, and simply by mapping the same area at three different wavelengths that you can see here, you can highlight one by one the individual materials. And of course, if you combine these three images together, you get this so-called compositional map, and you see nicely with high resolution the distribution of individual components. Of course, you can also extract do some statistics and analyze the data with the help of dedicated software tools. All right, this is another example of a polymer. This is a mixture of polystyrene and PMMA. And here you can see again how the optical contrast is changing when you tune the laser. And this is the combined chemical contrast. The resolution here, it's better because the tip was somehow sharper. But what I want to emphasize is that you don't obtain only the chemical maps, but in the same time you obtain, of course, the topography information, so the height, but also the mechanical phase, which is related to the stiffness of the material, and you can do an let's say a more advanced investigation on the mechanical properties of the material. Now, this is another project that I like. I did some measurements in the past for a collaborator from Czech Republic. He was synthesizing some polymer brush for functionalize some Teflon and make some artificial blood vessels. Now, he thought this material is it's homogeneous. But at the nanoscale, we could observe that it's not really that homogeneous. This is an image of the topography on the left side, and this is the reflectivity image on the right side. When I was imaging this polymer brush, here I did a scratch on the silicon, so the silicon is brighter, and of course the same you see in the AFM map, that there is a height difference between the two materials. But when you make a zoom-in image, you see that there are some domains in the topography, and the reflectivity and absorption show also a very clear contrast of these domains. So we thought that this functionalization, maybe it's not homogeneous, maybe it's not everywhere, but in fact, we realized that this polymer brush comes with different orientations, so different conformations in the same time. And although the deposition was everywhere, these different conformations could be seen in the nano-FTIR spectra. So taking spectra on the so-called hill and on the valley will reveal the spectrum of this polymer, polyethylene oxide. But you see there are some differences, and this comes, of course, from the conformations. Now, it was possible to deconvolute this spectra and to to give some information about the different conformations and distributions of the same polymer across this substrate. All right, this is an older example that I want to share with you. These are some measurements that I did 10 years ago. It's on pentacene. This is an organic semiconductor that it's used in flexible screens nowadays. And this is a topography image, an AFM map of this crystalline polymer. And we knew that the absorption, it's around 900 wave numbers. So taking a map, an image of this polymer, we got a very strange contrast. And this is very different from the topography. It's the same area, but you see there is absolutely no correlation between the optical contrast and the topography. We didn't know the reason. So we measured spectra on the different locations, on the bright and on the dark areas. And then we could realize that there is a shift, a very, very small shift of only 3 wave numbers. So mapping this polymer at this wavelength, you can invert the contrast by tuning the laser here. And we realized that this is a polymorph. These are 2 crystals, different crystal structures, slightly different, but enough to change the infrared properties. And because we could observe the distribution of this bulk phase and thin film phase at nanoscale, we could publish this at Nature Communication at that time. Looks like there is a big community working with such organic semiconductors, and the change in the crystal structures makes a big difference in the conductivity of such polymers. Now, not only polymers, but also organic biomaterials can be measured. And these are some results which I measured a couple of years ago. Here I would like to say that it's possible to scan very soft organic materials. These are lipid bilayers. And you see the topography image, and this is a line profile. And you see very nicely the thickness is about 5 nanometers. But what is important, this spectra, they look a bit noisy, but in reality, every absorption line, it's real and corresponds to this oriented phospholipid bilayer. Now, this is an older measurement which is done on proteins. And here we can see nicely not only the topography and the spectra specific to the proteins, but also the chemical mapping. This is an image done at 1660, highlighted the amide 1 band. And you can see that the same area, if you measure at 1720, the contrast is totally gone. Now, the sensitivity of the technique, it's really, really good. And I could measure even single proteins and could also map something like amyloid fibrils from Alzheimer's disease that show aggregation. I'm not going to present this data here because of the time restrictions, but I want to show you something else. These are measurements which are done on neurons, because maybe some of you are interested if this technique works on cells. And here we can see the cantilever in contact with the sample. And of course, you can decide which area you would like to focus on. And here are some images. This is the topography map, and you can see some dendrites. but in the same time, some crystals from the buffer. And on the right side, these are the reflectivity and absorption maps at 1660 wave numbers. This is exciting the amide 1 band alpha helical secondary structure of the proteins. Now, if you take spectra on different locations, you observe something like this. And we know that depending on the wavelength that you excite these proteins, you can map the alpha helical or beta sheet distributions. This is very important because in the Alzheimer neurons, there is so-called aggregation of proteins, and then you have a more beta sheet secondary structure proteins than alpha helical. In this case, we tune the laser and we make the same image, the same location at 1636. And here we can see the distribution of these aggregated proteins is different compared to the alpha helical. All right, this is, let's say, more on bio, but also something, some people I know that are looking into bio minerals. So it's a mixture of organic and inorganic. These are measurements that I did on the tooth. And you are at the interface between dentin and enamel. And this is a collaboration with some medical doctors from Munich. They were asking if it's possible to see the interface between these two tissues. And of course, in the sample prep, it's good. So there is not a very large roughness. You can see very nicely, not only the topography, but also in this case, the reflectivity and absorption. These maps are done at these specific wavelengths, which are matching the phosphate excitation. These are the highlighting the hydroxyapatite calcium carbonate from the tooth. So you can see very nicely from this contrast that you have a higher concentration of this hydroxyapatite in the enamel. And you can also see some crystals which have a higher concentrations of hydroxyapatite in this at this interface. Now, the same can be applied to human bones, and yeah, just by tuning the laser, you can map, in this case, the collagen distribution, which comes simultaneously, of course, with the topography information. All right, the same working principle, only that you map different components. So I'm not going much into the details. Another important topic, many people that I met are interested in corrosion. This is very important nowadays because I think 3 to 4% of the worldwide GDP, it's lost every year because materials corrode. And of course, we try to understand how this corrosion happens, and it starts with the nanoscale. But in the same time, there are some publications with this technique showing ways how to prevent corrosion by developing some functionalization. Now, just to keep it brief, here I want to show you a large copper sample. You see, this is a few centimeters. This is an image of the sample showing the cantilever on top of a heavily corroded area, and this is a less corroded area. Now, we did images, and this is what you observe at the nanoscale. In the AFM height, you get some particles on top of the surface, and of course, these are some corroded products. And you can, of course, take spectra of individual products or grains, or you can do a mapping and you see the distribution. And you see very nicely, in this case, the copper oxide and copper formate. By changing the laser that you are mapping, that you're using for this mapping, you can highlight the oxide or the formate within this image. Okay, another, let's say, important topic for this nowadays research is, of course, on the lithium batteries. And although this paper is a bit old, it's from 9 years ago illustrates very nicely that you can map and you can also measure spectra and follow chemical processes on very, very small particles. So you can do some kind of nano catalysis. You can observe the changes. In this case, this is the lithiation process, which happens during discharging of a lithium-ion battery. So you can measure the spectrum of such a grain, such a crystal, and see how efficient, let's say, was the charging or discharging. Now, this is something more recent. This is a paper from last year or 2 years ago, 2022 in Nature.com. And this is a more fancy battery system. And then with the help of the nano FTIR spectroscopy, you can also map and measure the same process of materials, charging and discharging. Perovskites, I know many groups are, of course, trying to obtain information regarding grain boundaries, perovskite grains at the nanoscale. And this is a measurement which I did quite fast, quite recently also. And here you can observe the topography image. I call red and green area because I don't know exactly what was the difference in this perovskite, but you see a clear contrast difference and the distribution of the variation of the chemical composition from the grains to the grain boundaries in this perovskite sample. Okay, now I have a few more slides to share with you, and I would like to present some work that has been done on 2D materials with this technique. And I would like to show you first the first publications that were made with this neaSCOPE instrument. This is like from 12 years ago. And in these Nature papers, people could observe so-called plasmon-polariton interference in graphene. So what it happens, I said that we generate a small nanofocus at the end of the tip by simply illuminating with the light. But this nanofocus has a very strong momentum, which excites these polariton waves in a way it's like waves on the water, which propagates and then reflects back at the tip. And then when you are scanning such graphene flake, you observe in different locations the interference between these polaritons. This is very important for optoelectronic devices, and the SNOM, it's one of the best techniques for making this characterization of the 2D materials. Now, to come to something which is more recent, let's say, that was developed quite recently in our labs in Munich. This is also a 2D material flake. It's molybdenum, actually it's tungsten selenite. These are also polaritons here, but they are excited not in the infrared, but in the visible. So you can see these so-called exciton polaritons propagating on the flake. And we can also measure not only the SNOM, the near-field optical response, but also we can do Raman and also PL spectra on the same flake with the same instrument. Another highlight I want to share with you is that all these measurements that I presented can be done also at very low temperature, something below 10K. So with the same high resolution and with the same classes of lasers, visible, infrared, but also terahertz. Maybe this is not interesting for biomaterials or for polymer science, but definitely for materials like 2Ds, for phase transition materials, this is very interesting to have this possibility for cryogenic measurements. And the sample, as well as the parabolic mirror, the AFM tip, it's contained by this cryostat, and this is working without liquid helium, so it's called dry cryostat. So maintenance costs are relatively quite low, let's say, compared to a classical cryostat working with liquid helium. Now, just to show you a quick example, this is again some 2D material. It's molybdenum sulfide crystal, and this is a topography image. And here we can see again some exciton polariton propagating, and the excitation is, as you can see, the visible range. Now, this contrast corresponds to what was measured before with the same instrument, let's say with the room temperature device, where we can see this propagation of the exciton polaritons. This was published in Nature Photonics. Now, I told you that this setup can go down with the temperature. So this was the measurement done in the room temperature, and this is measured at 70 K, and this is measured at 8.1 Kelvin. So you can see very nicely that this cryo neaSCOPE system detects very strong temperature dependence of this exciton polariton in the molybdenum sulfide sample. And of course, we see not only the optical amplitude, but we also get the optical phase, which is relevant for these 2D materials classes. Now, I want only to show this slide with publications which are measured on the 2D materials. And I have to say that some of these publications were measured with the setups that are installed here in Melbourne. Okay, I should update this with more papers, but there is no space on the slide anymore. So you have to believe me, there are actually more than 100 high-ranking papers on 2D materials with this technique. Okay, as a summary slide, there are many different measurement modes that can be done with this instrument. And today, of course, I only mentioned the AFM, the mechanical properties, but there are more that can be done with the system, like KPFM, piezo force microscopy, tip force. I show you some nanoscale infrared images done with the SNOM, so the Near-Field Optical Microscopy, but also with the AFM-IR, which is the photothermal technique. I'll show you some spectra that were recorded with the non-FTIR, and very briefly, possibility to do Raman and photoluminescence measurements. But just for you to know, it's possible also to measure simultaneously near-field photocurrent measurements, to do something similar also in the terahertz spectral region. You just need to have a terahertz laser, and then you are able to do these nanoscale measurements in this terahertz. But also, some people have fancy laser systems which allow to do time resolve pump probe measurements, and this is of course possible with the nanoscale resolution. When it comes to applications, I just briefly introduce you some examples on composites, on biomaterials, on polymers, and 2D materials. More it's possible in the field of semiconductors to map and to extract free concentration, the concentration of free carriers on semiconductors, or in plasmonics, when people are looking to map electric field mapping in waveguides or nanoantennas. All right, this is my last slide to briefly introduce, let's say, the company. Neaspec, it's a spin-off, Max Planck Institute from Munich. And since 6 or 7 years ago, we are purchased by Attocube. So now we are a business unit in Attocube. We are located in Munich. This is our headquarters. This is an image of a user meeting that we did like 2 years ago. There was a workshop. And I'm happy to say that here in Australia, we work together with Warsash Scientific, and we have Daniel Day here in the audience today. So, of course, for any inquiries regarding our microscopes, Daniel is happy to help. But also, I'm also here to talk with you in case you have any interesting sample that you would like to try, you would like to see any results. Please get in touch with Anders or Elena, and we can organize some test measurement on your sample to demonstrate what we can do. So with this, I would like to thank you for your attention, and of course, if there are any questions from the audience, I'm happy to answer.